2.1 Patterns and Inductive Reasoning. Our objective is to use inductive reasoning to make conjectures. Definitely some new words going on here. All right, it says you can observe patterns in some number sequences and sequences of geometric figures, and that's going to allow us to recognize relationships. Now, you've seen this before in algebra, so let's look at our first problem here. We're supposed to look for a pattern, and what are the next two terms in each sequence? So our first one says 3, 9, 7, 81. What's the pattern here? Well, each term is 3 times the previous term. That's the pattern. 8 times 1 is 3, or 3 times 3 is 9, 9 times 3 is 27. Our next two terms, 81 times 3 is 243, and 243 times 3 is 729. So those would be our next two terms. We would just continue to multiply by 3. All right, and B. Well, let's look. We have circles, and the first one has a triangle, and then a square, and then a pentagon. So what it looks like is that each polygon has one more side than the preceding polygon. So after this, we would have 6 sides for a hexagon, and then 7 sides for a septagon. So we go 6 sides and then 7 sides. Okay. Pause the video and do the next problem. All right, those were kind of fun. Our first one, we have 45, 40, 35, 30. So it looks like we are subtracting 5 each time. So 30 minus 5 is 25, and then minus 5 would be 20. So our next two terms are 25 and 20. Now the next one, we start with a square, and then we draw another square that's rotated 90 degrees inside of it, and then we have another square that's rotated 90 degrees inside of it. So we're going to draw another square rotated 90 degrees, and the next one just has another square inside of it. All right, well, those are entertaining, but what happens if we want to find the 10th or the 100th term or the 1000th term? Instead of drawing 10,000 patterns or 10,000 terms so that you can find the next one, you look for a pattern and make a conjecture. All right, and this here's a vocabulary word for you. A conjecture is a conclusion that you reach using inductive reasoning. So let's look at a problem here. We have circles. What conjecture can you make about the number of regions if you use 20 diameters? All right, so let's look at our circle. We draw one diameter. There's our first diameter. How many regions do we have? We have 2. What if we draw 2 diameters? 1, 2, 3, 4. What if we draw 3 diameters? Then we have 6. So 1 diameter forms 2 regions. 2 diameters, 4 regions. 3 diameters, 6 regions. Right? So we want to make a conjecture that relates the number of regions equals something to do with the number of diameters. So if we notice here, 1 diameter is 2 regions. 2 is 4, 3 is 6. So we can make a conjecture that each circle has twice as many regions as diameters. So the number of regions simply equals 2 times the number of diameters. And that forms a rule. If you remember from algebra, that's going to form a rule. So y would equal 2x, or r would equal 2d. So our 20 diameters, so the number of regions would equal 2 times 20. So if we have 20 diameters, then we have 40 regions. All right, go ahead and pause the video and do the next problem. Okay, what conjecture can you make about the 21st term? And we see that we have RWB, RWB. Hopefully you realized that these are in sets of 3. And so we are looking for 21. We know that 21 is a factor of 3. So if we look at, we know the 3rd, 6th, 9th, 12th, 15th, 18th, and the 21st term, we know that 19, 20, 21 is going to go RW, and so the 21st term is going to be B. Okay, good. Now, something to remember, it's important to gather enough data before you make a conjecture. If you only have a sequence like 1, 3, what could the next term be? Well, are we adding 2? Are we multiplying by 3? Both of those would be options. If we're multiplying by 3, the next term is 9. If we're adding 2, the next term is 5. So let's look at our example here. What conjecture can you make about the sum of the first 30 even numbers? So we're going to find the first few sums and look for a pattern. So we have our number of terms. You can make a table. Tables are always a good way to do things. And if we only have one term, that's just a 2. And then 2 terms, we are talking about the sum of the numbers. So 2 plus 4, those are even numbers. And then we go 2 plus 4 plus 6, that's 3 terms. 2 plus 4 plus 6 plus 8, that's 4 terms. Now let's look at the sums. 2 is just 2. 2 plus 4 is 6. 2 plus 4 plus 6 is 12. 2 plus 4 plus 6 plus 8 is 20. How can we relate that to the number of terms? Well, if you look over here, the number of terms 1 times 2 is 2. 2 times 3 is 6. 3 times 4. So we have the number of terms times, and where does this number come from? Well, that's the number of terms plus 1, right? 1 times 1 plus 1. 2, this is just 2 plus 1. 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1. So our pattern is the number of terms times terms plus 1. So we can conclude that the sum of the first 30, that's how many terms, would be 30 times 30 plus 1, which is 31, which is 930. So that makes it a lot easier. We could do the first 1,527 terms and get an answer without doing all of the math. That would be a lot of math. All right, pause the video and try the next problem. All right, this was kind of a neat one. You wrote down your number of terms, and then we did 1 and 1 plus 3, 1 plus 3 plus 5, because we're talking about the sum of the first 30 odd numbers. And we end up with 1, 4, 9, 16, 25. And hopefully you recognize those as perfect squares. It's always good to be able to recognize your perfect squares. Up to a minimum of 15. 20 would be better, but you should know your perfect squares up to 15 times 15, which is 225. So, well, how do I make this? 1 times 1, 2 times 2. Notice this is just the number of terms. So our pattern here, the sum of the odd numbers is the number of terms squared. So if we're going to make the first 30 terms, we would just do 30 squared, which equals 900. That was good. Okay. But we have to be careful. Remember up above, we said you have to make sure you have enough data. So let's look at our example here. We're talking about the sales of backpacks. And we have a graph here that shows us November, December, January, February, March, April, May, and the number of backpacks. So we have the number of backpacks versus the month, compared to the month. And what we see is that it decreases. And so we want to make a conjecture about what's going to happen in May. Well, if we continue to follow this trend, right, we can draw a trend line in here. In May, we're going to say it's going to decrease. And June, July, August, by the time we get to August, they are going to have negative backpack sales. Now, what do you think about that? What we see here is that the sales are decreasing by about 500 backpacks each month. And so if April had about 8,500, we can estimate, subtract 500 from that. In May, there's probably going to be about 8,000 backpacks. So go ahead and look at the next two questions. Pause your video and think about what your answers to those are. Okay, well, what conjecture can you make about the sales in June? We could make the conjecture that they're going to decrease. But the next question asked you, is that reasonable? And if you think about, well, when are backpacks sold? What drives the sale of backpacks? Well, what are backpacks used for? Camping. People go camping or hiking. And a lot of backpacks are sold for back to school. So this is probably not reasonable to assume that this trend is just going to continue and the company's going to go out of business. You have to think about what factors, even if you have a lot of data points like we did, what factors are going to affect that. So it's good to remember that not all conjectures turn out to be true. You should test it multiple times. You can prove a conjecture false by finding one counterexample. A counterexample is an example that shows your conjecture is false. It makes whatever pattern that you have, that you think you have, it shows that pattern is not true. So let's look at some examples here. If the name of the month starts with the letter J, it is a summer month. Well, if you think about your months, you have June and we have July. Those are summer months. But then you keep going through your months, and January starts with J. January is your counterexample. It proves your conjecture false. Okay? So our conjecture is if the name of a month starts with the letter J, it's a summer month. And we say no, January. January is a winter month that proves your conjecture false. So we would say this conjecture is false. All right, what's the next one say? You can connect any 3 points to form a triangle. Now, the first thing you think of is probably, well, yeah, 3 points make a triangle. But what did we learn in the first lesson here? Points can be collinear. So if your 3 points are in a line, then you cannot form a triangle. Any other combination of 3 points will make a triangle. All we need is this one and only one to make our conjecture false. Let's look at the next one. When you multiply a number by 2, the product is greater than the original number. And you say, well, yeah, of course, 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. Those are all greater than the original number. 2 is greater than 1. 4 is greater than 2. 6 is greater than 3. Don't forget we have a whole rest of a number line. What if we do -4? -4 times 2 is -8. And -8 is not greater than 4. So we have more than one counterexample. We have the entire negative side of the number line that makes numbers that are less than if you multiply by 2. All right, it's your turn. Go ahead and pause the video and do the next few problems. Okay, if a flower is red, it is a rose. Well, some roses are red, some roses are not red. But our requirement is the flower is red, then it would be a rose. Tulips are red, hibiscus are red, peonies, I think they're called. Lots and lots of flowers are red. So there are multiple counterexamples for that. All right, the next one. One and only one plane exists through any 3 points. Well, we know that any 3 points, we have a definition from 1.2. It was a postulate, actually. We should fix that. Pretty sure it was a postulate. Postulate from 1.2 that said, through any 3 points, you can draw one and only one plane. So that one's true. We have a postulate that confirms that. All right, and the last one, when you multiply a number by 3, the product is divisible by 6. Now, this is one of my complaints about the book. It should be evenly divisible by 6 because you learned back in like 4th grade, you can divide any number and you get a remainder, which is a decimal, right? You can turn it into a fraction or a decimal. So what the book is actually asking, and if it's going to ask this, it should ask this properly, because in geometry we assume nothing, right? The product is evenly divisible by 6, or is divisible by 6 to make a whole number. That would be acceptable as well, that we would end with a whole number. So if that is the case, well, we look at our numbers. Well, 3 times 4, that makes 12. Well, yes it is. But what if we look at 3 times 5 is 15? 3 times 3 is 9. There are multiple values of multiples of 3 that aren't divisible by 6. So we can have many counterexamples there. We do have this one here that's true, though. It's one of our postulates. Postulates are accepted as fact. Go back and look it up. All right, well, that was a nice short lesson. So enjoy the homework. I think these are going to be kind of fun.